Well, in today's lecture, we're going to talk about mass spectrometry. So it's a really powerful technique used to fragment molecules into smaller pieces and to analyze what the molecular weight is of a compound. So if you look down here below, here's just a general diagram of one version of a mass spec. So here we have an inlet and your sample's traveling through. And that's done either by injecting directly into the mass spec, or often these are hooked up to GCs, so there's already been some separation taking place in the GC column. As the sample travels through here, you end up getting an ionization by this electron beam. So it causes the molecule to be cleaved or fragmented into smaller pieces, and a lot of those pieces have a charge, and they're positively charged, and usually a charge of +1. They accelerate through this area, and then they enter an evacuated chamber that's subjected to a magnetic field. So what you have going through this vacuum here is a certain mass divided by charge, and usually that charge is a +1. So it's basically proportional to the masses here. Now it turns out that ions that are too heavy bend too little in this, and they fly off to the side and hit essentially the sides of the wall. So only ions that have the right mass travel all the way through and come down and hit the detector. And then we see a peak. And the detector is sensitive to the number of times these ions hit the detector. So it plots abundance, essentially. So by varying that magnetic field, we can, in essence, focus, and we can get ions that are too heavy to bend further down so that we can detect them on our mass spec. So let's take a look at electron impact ionization. So let's start off with something straightforward here, and let's define a few terms along the way too. So let's look at this molecule, methane. Okay, so methane travels through the GC, whatever, it's getting separated, it's making its way into the mass spec. And then what happens is we have a beam of electrons. What happens is that beam of electron comes in, and it basically kicks off one single electron. So then what we're left with is H connected to a carbon, 3 more, and then we're just going to put a single dot here with an H, and then I'm going to put brackets around this whole thing here, and a plus right here. And then we also kicked off a single electron. So that electron there is basically a lost electron. Now this thing here, that is called your radical cation. Right? So it's a radical and it's a cation, right? It's also known, so we'll say here, and it's also known as the molecular ion. And sometimes we abbreviate that M dot plus, or sometimes just M plus. So you'll see this. So for us, when we're looking at that, well, the mass to charge ratio is your M divided by Z. And that's essentially what's going to be plotted here. So for this, your M divided by Z is 16 divided by 1, or 16. So what happens next is we get fragmentation. So with fragmentation, we see a full cation being formed here. So what we get here is we get our carbon atom here with a positive charge plus H radical. All right. So a couple things about that. This thing right here is a fragment. So this is a fragment of that molecular ion. So for this, the charge is 1, right? So the mass to charge for that is equal to 15 because it lost a proton, right? So again, what we get here is we get our molecular ion. Sometimes we might write that as a CH4 bracket dot plus. We just wrote the Lewis structure there to be more clear. And then we get a further fragmentation into a full cation there. So when we look down here, we see this peak at 16. That's your radical cation. So that is your M plus, right? And that has your M to charge ratio, mass to charge, equal to 16. So that's also known here as your base peak. So there's your M plus peak there. And then we have fragments. Notice the base peak is the most prevalent here. Okay, so then if you lose that full H atom, then you come down here to M minus 1. So that is your M minus 1, and that has a percentage of about 85%. Okay, and so on and so forth. So those are the two most likely, and of course more challenging to lose more atoms on that one because you have a primary carbocation. Now the other thing I want to point out is this. So this is 16, right? That peak is 16. So this peak right here is 17. So how do you get up to 17? How do you have a molar mass bigger than its molar mass? Well, remember that carbon-13 is present in molecules. So that has a molar mass of 1 greater than, right, 12. And the relative abundance of carbon-13 is about 1.1%. So that's why you see that peak at 17 is 1.1. And we call this the M plus 1 peak. We'll gather some interesting information off of that as we go through and look at more complicated spectra and stuff. Let's take a look at what the actual spectrum looks like. So here's a mass spectrum of an alkane. So if we knew, for example, that we only had an alkane here, in other words, right, no oxygen or nitrogen or anything like that, we could look at the spectrum and we'd say this. We'd say, well, here's our parent ion, right? So that has a mass to charge ratio of 86. Now, if we didn't actually know that it was hexane, we would be able to play around with that molar mass right there of our molecular ion. So if we had, we'd guess here, maybe we have 7 carbons. So if you have 7 carbons, then that's 7 times 12. That'd be 84. So then that would leave you with a molecular formula of C7, right? 84 and 86 gives you 2, H2. That's unlikely, right? That's not a very reasonable molecular formula here. So we might guess 6 carbons. So 6 carbons gives us 72. 86 minus 72 is 14, so C6H14. And it turns out that that is the number of carbons and hydrogens for hexane. Right? But of course we know the structure because it was given to us here, but pretty soon we're not going to be given the structure, we're just going to be given the actual mass spec of this thing. Well, let's look down below and let's see if we can reason through some of the fragmentation patterns that we see here. So if you look at hexane down here below, you can see that we have these numbers, and these numbers represent what the molar mass of the cations would be if we were to fragment the molecular radical cation, right? So if we look at this first example down here below, if we cleave it at this point right here, right, at this point, then you end up with 2 parts. You end up with a butyl cation that has a mass to charge of 57 and an ethyl radical. Now that radical is not going to be detected because it's not charged. So that's the thing that we are going to end up seeing there. This also is equal to the parent ion minus 29. And so that 29 there is usually like an ethyl radical, right? Molar mass of 29, so you get a 57. Right? And then if we go down and look below, we could cleave it the other direction. So notice that the arrow is pointing, or the line is pointing the other direction here. And if we do that, then you'd get this ethyl cation, right? That would be detected. And then the butyl radical would not be detected, right? And then coming down below, here's your 43. So cleaving it this direction here, you get your propyl cation, right? And then lastly, looking down here below, we cleave at this position to that direction, and we get a 71 at that position. Now, if we look at the cleavage going to the right on this bottom one, you would, in theory, form this methyl cation, but that's going to be pretty unstable. So this is not detected and not really formed at all as far as the fragmentation is concerned. So that'd have a molar mass of 15, and when you look up here, we don't see anything here, right? So nothing's showing up there at all for 15. Okay, so let's take a look at the types of peaks that you actually are going to see. We've already seen the spectrum, so let's talk about the types. You have the base peak. So the base peak is the most intense and the highest peak. It's usually the most stable cation of fragmentation, right? You have your M peak. That's the molecular ion. That's your M plus peak sometimes. That's how we denote that. You have your M plus 1 peak. Now that's 1 unit higher than the parent peak, or your molecular ion. And remember, it's due to the presence of an atom that is one heavier isotope than carbon usually. So it's usually carbon 13 that we're looking at for that, generally speaking. And then the other one that I wanted to point out to you guys here too is this M plus 2 peak. So the M plus 2 peak is something that we always have to look at. So when I look at these spectra, when I look at this, I look at the M plus peak, and then I come over and I take a look at that M plus 1 peak right there. And I look to see if there's any percentages given to us. All right, and then I look to see, is there an M plus 2? I always do that before I start going through and analyzing the rest of the mass spec. Now, the M plus 2 tells us something interesting. Of course, it's next to the M plus 1 peak, and it's due to lots of different isotopes. So the ones that I want to look at with you guys that you're going to see most frequently are bromine, chlorine, and sulfur. So what you're going to see is a peak pattern here that's characteristic of those particular isotopes. So if you're looking down here at a spectrum, and this is your mass to charge, it's your x-axis there, right, you're going to have some peak here, essentially that is your parent peak, right? That's your M plus peak. So then the patterns that you are often going to see is this. Let's look at bromine. So bromine says the M plus 2. So we're going to come over here and let's just label all of these as being M plus 2. All right, so if you have bromine, it's about as tall. So we're going to come over here, and of course it's not going to be perfect, but about. So if you have a peak that's M plus 2 here, so there's M plus 2. If it's about as tall, then we would suspect that it's the bromine atom there. All right. Next, looking down here, what about chlorine? Well, it's about a third, right, as large as the M plus. So, again, we're not going to get a ruler out, but we're going to come down to about a third. So this is another M plus 2, and here you would suspect that chlorine would be involved. And then lastly, looking over here, sulfur. M plus 2, larger than usual. So it's larger, usually 4%, and again, we're not going to get out rulers or calculators or anything in for that, but we're looking for a peak that's taller. So something like that. Now if you see that, again, there's another M plus 2, you suspect that sulfur is involved. So another thing to recognize here is iodine. There's a large gap at 127. So you see a big gap because that's the molar mass of iodine. And then we'll talk about nitrogen down below. So there's a rule with nitrogen too. So the nitrogen rule. So in addition to looking at your molecular ion, your parent ion's molar mass, N+1 and N+2, I actually then take a look at what the molar mass is of the actual compound. So it turns out that if your mass to charge ratio here is odd for your M peak or your M plus peak, right, then there must be an odd number of nitrogens. If M by Z is even, there's either no nitrogens or an even number of nitrogen atoms. Now often we're given other data, so we can sometimes detect the presence of nitrogen based on, for example, what the IR spectrum looks like. But if you have an odd molar mass, that's usually a wink wink that you're going to have an odd number of nitrogens present. Now part of the idea of this odd even thing comes from the fact that you're really, when you put a nitrogen in, you're losing one H atom when you add one nitrogen. So if you look at this trend over here, CH4 is an even number, right, for carbon. You have 4 H's, that's even, so that's going to give you an even molar mass. Right? If you take off an H and put a nitrogen on and put 2 hydrogens there, then you end up having an even number, right, plus an odd number of H's, and an even number gives you an odd down there. So that's kind of where that comes from, that rule for nitrogen. And lastly, the other type of mass spec that you see is something called high resolution. So we saw before molar mass, for example, hexane, it was listed as being 86. But we can get more precise measurements too. So for example, if you got a molecule with a molar mass of 44, it could be a variety of different compounds that have molar masses that are really either 44 or very, very close to 44. Now, if we knew that the exact mass was 44.029, then you can go through and you can start, fine-tuning your guesses a little bit on that. So, 44.06, all right, that's not 029. Well, this one looks pretty good, right? No such luck here and maybe not there. So maybe you guess this one before you move on with too much more analysis. And a lot of times these mass specs are connected to databases with precise molar masses. So once you inject your sample, it separates, for example, a mixture of gasoline into all the components, right? You get all these molecular ions as they pass through a GC and get separated. And then those numbers are then run through a database, and you either get the exact compound or narrowed it down to a couple of choices that you can use some pretty good reasoning to go through and figure out what the actual compound is.